Let us continue ionic equilibrium. In ionic equilibrium, we have discussed strong acid versus strong base titration. Strong acid versus strong base titration we have discussed. For that, we will draw the graph between pH and volume of sodium hydroxide added. Now we will take pH here. pH we have found for each titration at the certain intervals we have found pH. That pH we will take in this axis. Then from burette we added sodium hydroxide solution. That volume of sodium hydroxide solution added we will take here. Volume of sodium hydroxide solution added we are taking in x-axis. pH we are taking in y-axis. We are getting the graph. What is how the graph will be there? That we will see. The graph will be on adding sodium hydroxide solution, pH increases slightly. Near the equivalence point, pH increases sharply. Then increases slightly. Like this graph we got. Now, using this graph, what we can find? We can say equivalence point. Center point you take, center point. That center point we can call as a equivalence point. Center point we can call it as equivalence point. Okay, so this is what graph in the sense strong acid versus strong base titration graph we can say. Next we will go for weak acid versus strong base titration. Weak acid versus strong base titration we will take. Weak acid we will take a 25 ml, concentration 0.1 molar. Acetic acid we will take. Acetic acid. This we will titrate with a strong base. That concentration is 0.1 molar. That is sodium hydroxide. Okay. Now we will take what in the burette, in the sense sodium hydroxide solution in the burette, acetic acid in the pipette. That means we have to transfer into conical flask. So now what is the pH of this conical flask solution in the beginning? That we will see. What is the pH of conical flask solution in the beginning? That we will see. In the conical flask, what we have taken in the initially, in the sense acetic acid we have taken. That pH we will find acetic acid dissociating to give acetate ion and H plus ion. In all the carboxylic acids, from all the carboxylic acids, carboxylic group will donate H plus. Okay. So in this carboxylic acid, this carboxylic group is donating H plus. So we got a so and so anion and a cation we got. Now we have to find a concentration of H plus. From the concentration of H plus, we can go for pH of solution in the conical flask initially. Okay. Now, what is the concentration of acetic acid initially? 0.1 molar. 0.1 molar acetic acid we have taken initially. How much acetic acid is dissociating? X molar. So how much acetic acid remaining at equilibrium? 0.1 minus X molar. How much acetate ion is produced? X molar. H plus ion produced? X molar. Now we will take the formula Ka, acid dissociation constant. It is called equilibrium constant for this. This acid dissociation constant equal to acetate ion into H plus ion by acetic acid concentration. Now we will substitute a acid dissociation constant. The acid dissociation constant is we will take the given value is this much. Then this H plus concentration and acetate concentration is equal, therefore we will write H plus square. Then by acetic acid, how much, in the sense 0.1 will take this X, we will neglect it. 0.1 minus X, we will take it as 0.1. X we are neglecting. So we are calculating what, in the sense concentration of H plus we are calculating. Concentration of H plus comes out to be 1.32 into 10 power minus 3. 10 power minus 3 molar. Concentration of H plus we got. From this, we will find pH. pH is how much in the sense so and so. pH is this much. So pH of this solution is 2.88 we got. So in yesterday's class, we have taken what in the sense HCl versus sodium hydroxide titration. HCl how much we have taken means 0.1 molar HCl solution we have taken. For that case, we said HCl dissociates completely because it is strong acid. Therefore, what is the concentration of HCl? That is the concentration of H plus. Therefore, pH is equal to how much in the sense 1 we said. Okay. So concentration of HCl is equal to concentration of H plus, that is equal to 0.1 molar. Therefore, pH of solution is 1. Now here you see that acetic acid solution we have taken, that is 0.1 molar. In this case, HCl is 0.1 molar, acetic acid is 0.1 molar, both are having same concentration. Here concentration of H plus is 0.1 molar. But in this place, concentration of H plus is 10 power minus 3 molar. That means here concentration of H plus is less when compared to this because it is weak acid. It will not dissociate completely. It will dissociate partially. Therefore, only we are getting H plus concentration nearly 10 power minus 3, whereas here H plus concentration is 0.1 molar. Okay. Therefore, as it is strong acid, dissociates completely. Therefore, concentration of H plus is high. Weak acid dissociates partially. So, concentration of H plus is low. So, here pH is high, whereas here pH is low. Okay. Here pH we can say 1, but here we can say pH is 2.88. Okay. So weak acid versus strong base titration. In the conical flask, we are taking weak acid. That pH we have got, that is this much. Okay. So in the burette, we will take a sodium hydroxide solution. So volume of sodium hydroxide solution added initially. Volume of sodium hydroxide solution added initially is 0 ml. Now pH of solution in the conical flask is 2.88. 2.88. Okay. So we have taken acetic acid solution in the conical flask. Initially, we have not added any sodium hydroxide solution. What is the pH of solution in the conical flask in the sense 2.88? Now, let us add sodium hydroxide solution from the burette into the conical flask. Drop by drop, we will add while continuously shake the conical flask. Now, what will happen to the pH? That we will see. Now, we are adding sodium hydroxide solution continuously. We have reached the point 2.5 ml. We have reached which point in the sense 2.5 ml. Now, what will happen in the conical flask? That we will see. In the conical flask, we have taken initially what in the sense acetic acid we have taken. What we have added from burette in the sense sodium hydroxide we added from the burette. Acetic acid reacting with the sodium hydroxide to give what in the sense sodium acetate. Sodium acetate and water. Okay. So acetic acid, how much we have taken in the conical flask initially? 25 ml. 25 ml we have taken. What is the concentration of acetic acid? 0.1 molar. Let us multiply both. We will get millimoles of acetic acid. So acetic acid millimoles we got. It is the millimoles of acetic acid we can say. So how much millimoles of acetic acid we have taken in the sense 2.5 millimoles of acetic acid we have taken initially. So we have added sodium hydroxide now. How much extent we have added? 2.5 ml of sodium hydroxide we added. 2.5 ml. What concentration of sodium hydroxide? 0.1 molar. So how many millimoles we have added? 0.25 millimole. So 0.25 millimoles of sodium hydroxide we added into the conical flask. Okay, sorry. So 0.25 millimoles of sodium hydroxide we added. Now, here how much sodium hydroxide will react in the sense 0.25 millimole will react, therefore remaining is 0. How much acetic acid will react in the sense 0.25 millimole will react, therefore remaining is 2.25 millimole. 2.25 millimole of acetic acid is remain. How much sodium acetate formed in the sense 0.25 millimole of sodium acetate is formed. Okay. Now, what is the pH of resultant solution that we want to see? In the resultant solution, what is there? We have to see. In the resultant solution, what is there means acetic acid is there. Acetic acid is called a weak acid, we can say. And sodium acetate is there in the resultant solution. Sodium acetate, we can say, salt, we can say. It is a salt of what? This weak acid and strong base. Therefore, the resultant solution is what do you think? Shall we say that resultant solution is aqueous solution of weak acid? What shall we say? Is there any special name for this? Yes, this solution is what in the sense buffer solution. It is buffer solution. It is which buffer in the sense acidic buffer. For acidic buffer, how to calculate pH in the sense Anderson equation is there. That Anderson equation says that pH is equal to pKa plus log salt by acid. This is the Anderson equation. Okay, sir. Now we will substitute here pKa, we can write it as minus log Ka. Ka is 1.75 into 10 power minus 5. We will substitute plus log salt. We will substitute. This is this ratio salt by acid. This is concentration ratio. This concentration ratio we can even call moles ratio. Also we can call number of moles ratio. Also we can call because here denominator volume will get cancelled. They're both present in the same solution, so volume for both will be same. Therefore we need not substitute concentration, we need not substitute volume, we can substitute mole ratio, that is enough. Okay, so salt moles we will substitute. Salt how many moles means 0.25 moles, so that we are substituting. Then acid moles we are substituting, that is at after the reaction 2.25 millimoles is there, that 2.25 millimoles we are substituted. We are simplifying, we are getting pH how much in the sense 3.8 we got. Okay, so now we will write the pH how much in the sense 3.8. So after adding 2.5 ml of sodium hydroxide into the conical flask, the conical flask solution pH is how much means 3.8. Initially pH is how much means 2.88. On adding sodium hydroxide, pH increases. Why pH increases? Because we are adding base. Okay, so acid is we have taken acid in the conical flask, that is reacting with the sodium hydroxide. So concentration of acetic acid decreasing, therefore pH increases. Okay, so now we said pH of solution in the conical flask increases. Okay, let us continue adding sodium hydroxide solution. Suppose we have added still more 2.5 ml. So far we have added 5 ml. Now pH of solution is 4.15. Let us continue adding sodium hydroxide. Now we have reached 10 ml in the burette. That is pH is how much means 4.58. Then further add sodium hydroxide. We reached 15 ml. Now pH is 4.93. Further add sodium hydroxide. We have reached 20 ml. pH of solution is 5.36. Further add 22.5 ml. pH of solution is 5.7. Further add 23.75 ml. pH is 6.03. Continue adding. So we have reached 24 ml. Here pH is 6.14. Now further we are adding 25 ml. We have reached 8.73. So now we will see this point. This point we have got to 8.73. So we will see about this point. 25 ml sodium hydroxide added. No, that point we will see. Now we are going for which point in the sense 25 ml sodium hydroxide we added. That point we will take. Okay, so now in the conical flask, initially we have taken acetic acid. This acetic acid reacting with the sodium hydroxide from the burette solution added to give what in the sense sodium acetate and water. Initially in the conical flask we have taken 25 ml of acetic acid of 0.1 molar. Therefore initially we took 2.5 millimoles of acetic acid. Now so far how much sodium hydroxide we added from burette in the sense 25 ml we added. Concentration of sodium hydroxide is 0.1 molar. On multiplying we are getting millimoles of sodium hydroxide added so far. So far we have added how many millimoles of sodium hydroxide in the sense 2.5 millimoles of sodium hydroxide we added. Okay, now they are going for reaction. It is reacting 2.5, remaining is 0. It is reacting 2.5, remaining is 0. sodium acetate formed 2.5 millimoles. Sodium acetate formed, so 2.5 millimoles. Okay. Now in the resultant solution, what is there, that we will see. Okay. So now in the resultant solution, what is there in the sense 2.5 millimoles of 2.5 millimoles of sodium acetate is there. 2.5 millimoles of sodium acetate is there. What is the volume of resultant solution in the sense 50 ml? Why 50 ml in the sense 25 ml of sodium acetic acid we have taken initially. Sodium hydroxide we added 25 ml so far. So resultant solution volume is how much, means 50 ml we can say. Sir, now you say that now see that we have taken in this reaction, you see acetic acid remaining is 0, sodium hydroxide remaining is 0. That means complete reaction or not? Complete reaction in the sense this point is called which point? Equivalence point. Equivalence point we can say. Therefore, we can say this point is called a equivalence point we can say. Why do we say equivalence point? Because acid base reaction is completely over. Have we got idea? Therefore, here at this point is called equivalence point because acetic acid is reacted completely. That means neutralization is completed. Neutralization completed in the sense, what is the pH we have to get? You think it? Just previous class you think it HCl versus sodium hydroxide titration we have done. In that case, we got equivalence point. At equivalence point, what is the pH we got? 7 only, no? HCl versus sodium hydroxide titration. We got equivalence point. At equivalence point, we have found pH. What pH we got? 7. But in this place, it is also acid versus base titration only, but weak acid. Acetic acid versus sodium hydroxide. In this, we got equivalence point here. At equivalence point, what pH we have to get? Because complete neutralization, no? Complete reaction is completely over, no? Acetic acid is reacted completely, no? Sodium hydroxide also reacted completely, no? So what is the pH we have to expect? But how much pH experiment says? Experiment says 8.73. Experiment says 8.73 in the sense 8.73 in the sense basic medium, because we are considering temperature is 25 degrees Celsius. Temperature 25 degrees Celsius means neutral, means pH is 7. pH greater than 7 means basic medium. Here pH is 8.73. That means the resultant solution is not neutral. Resultant solution is basic. Why resultant solution is basic? What is the reason? What had happened here? In the resultant solution, what is there means sodium acetate is there. In the resultant solution, sodium acetate is there. This sodium acetate is having anion acetate. Acetate anion is from weak acid. Therefore, this anion can undergo hydrolysis here. This anion can undergo hydrolysis. So, anionic hydrolysis means resultant solution will be basic. Sir, here what about cation? Cation is Na+. It is from strong base. Therefore, it is not undergoing hydrolysis. No hydrolysis. That means in this titration, acid-base neutralization takes place in one side. Another side, the produced salt undergoes hydrolysis. From the salt, which part undergoes hydrolysis? Anionic part undergoes hydrolysis. Cationic part, no hydrolysis at all. Set. Here, anionic hydrolysis takes place. Therefore, we will take anionic hydrolysis. Anionic hydrolysis, anion plus water gives this anion takes H plus from water and gives acetic acid. And in water, what is the remaining means OH minus, that we will write. So acetate ion reacting with water to give acetic acid and OH minus, we can say. What is the initial concentration of acetate ion? Acetate ion is how much? How many million? How much? What is the initial concentration of acetate ion, that we want to know it? So for that we will see the salt. Salt is how much? 2.5 millimole. In this salt, how much is ionizing? That is the millimoles of acetate ion. How much sodium salt will ionize? Let us assume 100% ionization. Salt in the sense we can consider complete ionization. Suppose if they mention 60% ionization, in the sense you take that. Suppose if they mention 80% of salt is ionizing, means you take 80%. If that is nothing is mentioned, means take salt undergoes complete ionization. Okay, so we will take 100% ionization. Therefore, acetate ion is how much in the sense 2.5 millimole will take. Acetate ion is 2.5 millimole. Okay. So acetate ion, how much is there? 2.5 millimole is there. We will consider. Okay, and how much undergoing hydrolysis? How much undergoing hydrolysis in the sense we will consider x millimoles undergoing hydrolysis. Therefore, how much remaining at equilibrium means 2.5 minus x millimoles remain. How much acetic acid produced in the sense x millimole? How much hydroxide produced in the sense x millimole we can take. Now we will go for equilibrium constant. The equilibrium constant is called hydrolysis constant. This hydrolysis constant is nothing but Kw by Ka. Kw by Ka we can say. Kw is called ionic product of water. Ka is called acid dissociation constant. It is equal to concentration of acetic acid by concentration of OH minus by concentration of acetate ion. Concentration of acetate ion we can say. Now we will substitute Kw. Kw is 10 power minus 14. Ka is called acid dissociation constant of acetic acid. Ka for acetic acid is how much in the sense 1.75 into 10 to the power of minus 5. Then acetic acid and OH minus concentrations are equal. Millimoles of that is we will write concentration of OH minus square we will write by acetate ion we will take. Acetate ion is how much in the sense 2.5 minus x. Now I will neglect this x. I will neglect this x. I will take 2.5 only. So 2.5 millimoles by volume of resultant solution is how much in the sense 50 ml. That 50 ml I will substitute. Okay, here 2.5 millimoles. So it is 2.5 millimoles. It is volume of resultant solution. So I got concentration of acetate ion. I have substituted. From this I can get concentration of OH minus I can get. Okay, so we are getting a what in the sense concentration of OH minus we are getting. That is how much we will see. So concentration of OH minus is equal to this. We can do in another way. Sorry, okay. Concentration of OH minus we are getting. That is how much in the sense 0.5345 into 10 to the power of minus 5 molar. From this we have to get H plus concentration in order to find pH. Now we will take Kw is equal to H plus into OH minus. Kw value will substitute, that is 10 power minus 14 into H plus concentration. OH minus value we are substituting 0.5345 into 10 to the power of minus 5. Now we are getting from this H plus concentration we are getting. H plus concentration is how much in the sense 1.87 into 10 to the power of minus 9. From this we are going for pH. pH is equal to 8.73. Okay. Now you see that why pH we got 8.73? Because salt hydrolysis. In the salt, which part undergoing hydrolysis? Anionic part is undergoing hydrolysis. Okay. Therefore, only pH is 8.73. Okay. So in this case, we have discussed weak acid versus strong base titration. At this equivalence point, pH is greater than 7 because from the salt, anion undergoes hydrolysis. Therefore, we got pH is greater than 7. We got. Sorry. Okay. Next, let us continue adding sodium hydroxide solution. We are continuing adding sodium hydroxide solution. We have reached 26 ml. That means so far we have added 26 ml of sodium hydroxide solution. Now, what is the pH of solution that we will see? So far we have added how much sodium hydroxide solution? 26 ml we added. Set. Now, what is the pH of solution? We will see. Okay. Now, in the conical flask, initially what we have taken in the sense acetic acid we have taken. What we are adding from burette in the sense sodium hydroxide, acetic acid reacting with the sodium hydroxide to give what in the sense sodium acetate and water. Initially, how much acetic acid you have taken? 2.5 millimoles we have taken. So far we have added how much sodium hydroxide in the sense 2.6 millimole. That means 26 ml we added. 0.1 molar concentration. So 2.6 millimole of sodium hydroxide we added. So acetic acid reacting 2.5 millimole, remaining is 0. Sodium hydroxide reacting 2.5 millimole, remaining is 0.1. Okay, sir. Now sodium acetate formed 2.5 millimole. Sodium acetate formed 2.5 millimole. Okay. Now what is the pH of resultant solution? We have to see. In the resultant solution, what is there? First we will take. In the resultant solution, what is there means sodium acetate is there. Sodium acetate is there and sodium hydroxide is there. Sodium hydroxide is there. That means in the sodium, from the sodium acetate, what will be there means acetate ion and Na plus. Sodium hydroxide contains Na plus and OH minus. Now, what is the possibility in the sense here? Acetate ion can undergo hydrolysis. Therefore, acetate ion plus water gives what in the sense acetic acid, and OH minus. This hydrolysis is possible. Okay. Now, in this one here, sodium hydroxide is there in the resultant solution. This sodium hydroxide gives OH minus ions. Due to sodium hydroxide, concentration of hydroxide is high. Therefore, here backward is favoring. Okay. Therefore, in this case, position of equilibrium, and in this case, position of equilibrium. Here, sodium hydroxide is not there. Only sodium acetate is there in the resultant solution. From the sodium acetate, acetate ion is undergoing hydrolysis, we said. But in this case, in the resultant solution, sodium acetate is there as well as sodium hydroxide is there. The sodium hydroxide is giving common ion OH minus. Because of common ion effect, here backward is favored. Backward is favored in the sense position of equilibrium is towards left. Towards left we are saying. Okay. Therefore, in this place, concentration of OH minus, you see how much we got. What is the concentration of OH minus we got? 10 to the power of minus 5 millimole. 10 to the power of minus 5 molar. Here concentration of OH minus is in this place 10 to the power of minus 5 molar. Sir, now we will see, first we will find a concentration of OH, sodium hydroxide we will find. Then we will see about a concentration of OH minus from the hydrolysis of acetate ion we will see. Okay, sir. So first we will see sodium hydroxide concentration we will see. Sodium hydroxide concentration is equal to sodium hydroxide millimoles by volume of resultant solution 51 ml. Okay, so this concentration we will find now. First, this concentration is we got this much 0.1 millimole by 51 ml. It is the sodium hydroxide concentration. This is nothing but concentration of hydroxide from sodium hydroxide. Now we will see here over the what is the value do you think? X is less than 2.5 millimole. In denominator 50 ml will be there. Concentration of hydroxide is 10 to the power of minus 5. Concentration of hydroxide is 10 to the power of minus 5 due to anionic hydrolysis. Now here sodium hydroxide alone is giving how much you see. Okay, this concentration is greater than this value, no? Then hydroxide concentration is here due to anionic hydrolysis. Hydroxide concentration is less than the previous case, no? Therefore, we need not consider anionic hydrolysis here. Sodium hydroxide concentration itself is enough. Actually, anion also giving OH minus, no doubt. But that concentration, if we add, we cannot simplify, because in the previous case itself we have neglected some term. Therefore, simplifying is difficult. Therefore, we are neglecting this OH minus concentration provided by acetate ion when compared to this OH minus. Okay, sir. So we got OH minus concentration. From this OH minus concentration, we are going for H plus concentration. From H plus concentration, we are going for pH. pH is how much in the sense 11.29. Okay, so we got pH of resultant solution. pH of resultant solution, how much we got in the sense 11.29 we got. Okay, then we will add sodium hydroxide continuously. We are reaching 28 ml while we are calculating pH, that is 11.75. Continuing adding sodium hydroxide 30 ml we got. Now pH we are seeing that is 11.8. So we got like this pH. Now we will see how the pH is changing on adding sodium hydroxide solution, that we will see. Okay, sir. Here we will see that here 2.5 ml we added here. How much pH is rising means nearly 1. Here 2.5 ml we added. How much pH is rising in the sense roughly 0.4. Here 5 ml we added. How much pH is rising you see roughly 0.4. Here 5 ml we are adding. How much pH is changing? Roughly 0.4. 5 ml we are adding. pH changing roughly 0.4 or 0.5. Here we are adding 2.5 ml. 2.5 ml only we are adding. How much pH is changing means roughly 0.4. Here how much we are adding? See, just 1.25 ml. How much pH changes? You see that roughly 0.3. Here how much we are adding? 0.25 ml. How much pH is changing? See, nearly 0.1. See, we are adding just 0.25 ml only, but pH changes how much? 0.1 only, roughly 0.1 only. Here 1 ml we are adding, pH is changing how much you see? Here 1 ml we are adding, how much pH changes you see that roughly 2.5, roughly 2.5 pH changes. That means near the equivalence point, how the pH is changing you see that, okay, roughly 2.5. Then 25 ml to 26 ml means we added 1 ml. That means how much pH is changing you see that roughly we can say roughly 2.5 to 3. Here 2 ml we are adding, pH changes just 0.5. Here 2 ml we are adding, pH changes just 0.05. That means where pH changes drastically near the equivalence point. Sir, okay. pH changes drastically near the equivalence point. Now here pH goes on increasing near the equivalence point. Drastic change is there, but how the increase in pH is there here when compared to the previous titration, strong acid versus strong base titration? Increase in pH here is less when compared to strong acid versus strong base titration. Then near the equivalence point, pH changes. The change in pH near the equivalence point here is less drastic when compared to strong acid versus strong base. Therefore, how the graph will be there for this weak acid versus strong base titration? That if you see here, graph is like this. No, it is strong acid versus strong base. But weak acid versus strong base titration in the sense how the graph will be there in the sense starting point will be like this. Starting point will be like this. Why starting point is like this? Because initially pH of conical flask solution is high when compared to strong acid. Therefore, like this. Then the graph is going like this. The graph is going like this. Going like this. It will go. It will go like this. It will go like this. Then it will go like this. Okay. Now here center point is equivalence point. Center point is equivalence point. Okay. Volume of sodium hydroxide. pH of equivalence point is greater than 7. pH of equivalence point is greater than 7. So here a sudden increase in pH for this weak acid versus strong base titration, sudden increase in pH near the equivalence point is less when compared to strong acid versus strong base titration. Okay, sir, like this is there we are saying. Sorry, we got the graph. Now we will see what is the suitable indicator for this titration, that we will see. Now for this acetic acid versus sodium hydroxide titration, what is the suitable indicator? Which acid base indicator we can use? That we will see. First we will take phenolphthalein. We will take, okay, we are taking phenolphthalein. Phenolphthalein pH range is 8.3 to 10. Up to 8.3, phenolphthalein gives colorless. From 10 onwards, phenolphthalein gives pink color. Okay, so now we will see. Let us add phenolphthalein here. Phenolphthalein gives colorless. Now colorless only, colorless only, colorless only. Here also colorless, here also colorless. Now up to this, phenolphthalein gives colorless. Up to this, phenolphthalein is colorless only. Phenolphthalein is colorless only. Okay. Now here in the sense, phenolphthalein gives light pink. Phenolphthalein gives light pink color. Okay. Here in the sense, only pink color will be there. Only pink color will be. Then onwards, only pink color will be there. Now say phenolphthalein gives color change near the equivalence point, shall we say? Yes. Therefore, we can use phenolphthalein is a suitable indicator for this titration. Okay. So for this titration, phenolphthalein we can use. Phenolphthalein indicator we can use. So phenolphthalein indicator we can use for this titration that we got. Next we will see. Next indicator is methyl orange we will take. Can we use methyl orange for this titration? That we'll see. Methyl orange pH range is how much in the sense 3.1 to 4.4. 3.1 to 4.4. It is methyl orange indicator. Here up to 3.1 methyl orange gives red color. From 4.4 onwards methyl orange gives yellow color. Okay. Now let us add methyl orange here. Methyl orange gives what color? Red color. Okay. Methyl orange gives red color. Here red color. Here also, here what will be there in the sense red plus yellow, red plus yellow. Okay, here what in the sense all the near to yellow, near to yellow. Here what color in the sense yellow color, yellow color. So this methyl orange shows change in color at where you see. Initially it gave red color, it gives change in color at this point. Where is the equivalence point? Equivalence point is here. Equivalence point at 25 ml, but methyl orange shows change in color at 10 ml. So can we use methyl orange indicator for this titration? We cannot use. We cannot use methyl orange indicator for this titration. Sir, okay. So methyl orange indicator is not suitable for this titration. That point we got. Next we will go for another indicator. Methyl red indicator we'll take. We are taking methyl red indicator. For this methyl red indicator, what is the pH range? That is 4.2 to 6.3 up to 4.2 red color. From 6.3 onwards, yellow color will be there. Okay, so now we will add a methyl orange here. Methyl orange gives red color here. Okay, red color. So in this place, red color. In this place, red color. Then here we'll see yellow plus red. Here also yellow plus red. Here also this red color plus yellow color. Here also yellow color and red color mixture will be there. Here we will see here nearly yellow color, nearly yellow color, nearly yellow color. Here we will see nearly yellow color. Here we will see yellow color, we can say. Here we can say yellow color, we can say. So this methyl red is giving yellow color at this equivalence point. Here if we see yellow color, then onwards yellow color. So shall we say methyl orange gives a distinct change in color at equivalence point, distinguished change in color at equivalence point. Therefore we can use methyl red indicator, we can use. Okay, sir, like this we have to select which indicator we have to use for the given titration. We have to select. Now I will take the indicator called malachite green. We will take the malachite green is having pH range how much in the sense 11.4 to 13. Okay, so 11.4 to 13, it is what in the sense malachite green. Malachite green, it is at up to 11.4 it is having green, then onwards colorless. Now you say whether shall we use this malachite green indicator for this titration or not. Is it suitable or not? You think and say. Sir, now we will check. First, malachite green indicator we will add into the conical flask solution. This malachite green is giving what color to the conical flask solution? Green color. So green color continues. Green color continues till where in the sense up to this plus green color will continue. Okay, up to this place green color will be continued. Then onwards what will happen? Green color plus colorless in the sense green color intensity decreases. Green color intensity decreases. Now we can say, isn't it? Therefore now green color intensity decreases where? At 28 ml. Equivalence point at where? 25 ml. So what is the difference? 3 ml is the difference. Is it called near the equivalence point? No. End point, is it called end point then? No. End point means what? Near the equivalence point. Near the equivalence point means how much difference should be there? 0.1 ml difference, 0.2 ml difference, otherwise 0.3 ml difference. But how much difference is coming here? 3 ml is coming difference. Then how can we use methyl orange indicator to find end point? End point means of course it is not equivalence point. End point in the sense it is almost closer to equivalence point, we can say. So difference can be end point and equivalence point difference can be 0.1 ml, 0.2 ml like this. But 3 ml means shall we say that this is end point? No. So that we cannot use malachite green indicator for this titration. Okay, so in this way only we have to select acid base indicator for the given titration. We have to select. Okay, set. So in this weak acid versus weak base titration, initially we have found acetic acid pH. So to find acetic acid solution pH, we have used what value in the sense Ka value we have used and we found pH. Then onwards, from year to year, we have considered the solution as what? In the sense buffer solution. We have considered the solution as buffer solution. At this place, we have considered annual